Hello, good evening all. I'm Saurabh and I welcome you to this session for the NPTEL course Applied Thermodynamics. This is our session number 11. In today's session, we will solve some problems from the module 5, that is refrigeration and air conditioning systems. So today we will solve some problems related to psychrometry. And as you know that psychrometry is the study of moist air, that is mixture of dry air and water vapor. Okay, so we will start now from question number 1. So question number 1 says, in case of evaporative cooling, the energy carried by injected stream is normally smaller in magnitude than either of two moist air streams. So you know that in case of evaporative cooling, you have some arrangement where air comes in. Air means moist air comes in, and there in the system you inject some water spray. Okay, that is nothing but injected stream, and at outlet you have cool moist air. Okay, so it is saying that energy carried by this injected stream is normally smaller as compared to these two moist streams, and we have to tell whether this statement is true or false. So as you know that energy carried by this injected stream is very small, because there is very less quantity of water which is evaporated. Okay, so the statement is true. Okay, so I hope this is clear and you can move to the next question. Okay, question number 2 says, at 100% relative humidity, the wet bulb temperature is. So you know what is relative humidity? There are two terms. One is relative humidity, another is wet bulb temperature. Okay, so if you know what these terms mean, then you can easily answer this question. Okay, so one is relative humidity. So it is defined as mass of water vapor in the moist air. Okay, and divided by maximum mass of water vapor that can be present here at given temperature. Okay, so at given temperature there will be some maximum mass that you can put in dry air. Okay, but the actual mass of water vapor will be lesser than that. So this ratio is called relative humidity. Okay, and what is wet bulb temperature? So wet bulb temperature, you know, is measured by some specific instrument. So how to measure that? It is very simple. For example, you have one thermometer. Okay, this is the thermometer. You put some cotton at this bulb. Okay, cotton, wet cotton actually. Okay, you just you just swing this thermometer. Okay, from this end, let us see. So what will happen? Water at this end, at the wall wet end, it will be evaporated, and because of evaporation, this will get cooled. So the temperature measured by this thermometer is called wet bulb temperature. So wet bulb temperature, you know, this will be less than your uh, ambient temperature that you can call as dry bulb temperature. So why this wet bulb temperature is less? Because of this evaporation, right? Evaporation that is taking place at this wet cotton. But if the relativity is 100%, relative humidity is 100%, then there will be no evaporation, right? Because already there is maximum water vapor present in the air. Okay, so you cannot add more water vapor into the air. So there will be no evaporation. And since there will be no evaporation, so there will be no cooling, right? So the wet bulb temperature will be equal to the dry bulb temperature, right? So wet bulb temperature will no longer be lesser than the dry bulb temperature. Okay. So at 100% relative humidity, the wet bulb temperature is there are four options. One is lower than the dew point temperature. Second is higher than the dew point temperature. Part C is equal to the dew point temperature. Okay. So actually at 100% relative humidity, the wet bulb temperature and dry bulb temperature will be equal, but here we had to compare with dew point. So I'm sorry. So now we will have to discuss what is, dew point. Okay. So first let us discuss what is dew point. I have discussed dry bulb temperature, that is not asked in this question. What is asked is dew point temperature. Okay. So this is our TS diagram. This is saturation zone. So for example, you have some temperature. Okay. This is our initial condition. Then you start cooling at constant pressure. So you'll have to move along a iso bar. Okay. For example, you start cooling like this. So this is an sorry. So this is in constant pressure line. And you start cooling. So when you reach at this point, at point 2, so at this point you have reached the saturation state, right? Okay. So the temperature at point 2, this is called the dew point temperature. Okay. This is called dew point temperature. And since at this point 2, we have reached the saturation state, so the relative humidity will be 100%, right? 100% relative humidity, right? So 100% relative humidity. So at this point 2, the wet bulb temperature will be equal to dew point, right? Dew point temperature, because this is our dew point temperature and the same is the wet bulb temperature, right? We have to focus over this point 2. Okay. This is 100% relative humidity, and wet bulb temperature will be same as dry bulb temperature because there is no evaporation. And since we are on this saturation line, so this dew point temperature and wet bulb temperature will be basically the same. Okay. So answer should be equal to the dew point temperature. Okay. I hope this is clear. So we have discussed three temperatures: wet bulb temperature, dew point temperature, and dry bulb temperature. Okay. So this you can think as a definition of dew point temperature. The dew point temperature is equal to the saturation temperature, T saturation, at this given pressure. Okay. So pressure is basically partial pressure. Okay. Partial pressure of water vapor. Okay. So at a given partial pressure of water vapor, whatever the saturation temperature is, that will be equal to your dew point temperature. Okay. I hope this is clear and we can move ahead. Okay. So question 3, it says in a typical sample of ambient air. So ambient air means something which you have taken from environment. And in environment, you know that you don't have dry air. You have mixture of dry air and water vapor. So basically, you have moist air in the ambient. Okay. So you have some sample from the ambient that is at 35 degrees Celsius, 75% relative humidity, and standard atmospheric pressure of 101.325 kilopascal. Okay. So we have moist air at 35 degrees Celsius, 75% relative humidity, and pressure is 101.325 kilopascal. Okay. So this is atmospheric pressure. That is a total pressure, right? Total pressure means partial pressure of dry air plus partial pressure of water vapor. Okay. So if the saturation pressure at 35 degree is 5 kilopascal, the amount of moisture in kilogram per kg of dry air will be approximately. Okay. So this sample has 75% relative humidity and saturation pressure at 35 degrees Celsius is given. Okay. So PS at 35 degree is 5 kilopascal. Okay. So you know what is relative humidity? We have discussed in the previous question. It is, you know, the mass of water vapor divided by the maximum mass of water vapor that can be, there in the air. Okay. So relative humidity is the actual mass of water vapor in the dry air or moist air divided by the maximum mass of the water vapor that can be present, that you can put in the moist air at the given pressure. Okay. So in terms of pressure, you can write it as PV, that is partial pressure of water vapor, divided by P PS, let us say. Okay. PS is the saturation pressure. Okay. So pi is given, relative humidity is given, that is 75%, and partial pressure we don't know, and saturation pressure at this given temperature 35 Kelvin, 35 degrees Celsius, it is given to be 5 kilopascal. Okay. So from here you can calculate partial pressure of water vapor. So, okay. So it will be 5 kilopascal multiplied by 0.75. Okay. So if you calculate this value, it will come out to be 3.75 kilopascal. This is the partial pressure of water vapor. Okay. What we have to find? We have to find the amount of moisture in kg per kg of dry air. So amount of moisture, moisture is basically water vapor. Moisture in kg per kg of dry air. This is nothing but, uh, specific humidity. or omega. Okay, so this is amount of moisture in per kg of dry air. Okay, this we have to find. So you can directly use the formula, or what you can use is mv divided by ma. So molar mass of water vapor, molar mass of water vapor multiplied by the number of moles of water vapor divided by molar mass of air into number of moles of air. Okay, and this thing you already know, and the ratio of number of moles is equal to the ratio of partial pressures, right? Because from the ideal gas equation, you know, PV is equal to nRT. So T is the mixture temperature, that is same for air as well as water vapor. R is universal constant. Okay, volume is, you know, anyway same for both. I mean vapor and air, because this V will be equal to the volume of mixture. So the ratio of moles will be equal to the ratio of partial pressures. Okay, so you can write it as the molar mass of water vapor. This you can take as 18 point something, 18 for our case. For simplicity, we will take 18. And molar mass of air is something around, I have taken 28.96. Okay, and instead of mole ratio, you can use pressure ratio, ratio of partial pressure of vapor and dry air. Okay, so partial pressure of water vapor, partial pressure of air. Okay, so partial pressure of air you have calculated. This is coming out to be 33.75. So I'm not writing the units because we are keeping the units same for all the quantities, so they will cancel out. Divided by 28.96, and partial pressure of air will be total pressure minus partial pressure of vapor, right? Partial pressure of air will be equal to total pressure minus partial pressure of vapor, correct? So total pressure is atmospheric pressure, that is 101.325, 101.325 minus partial pressure of this water vapor 3.75. Okay, so this will be the specific humidity. So we will calculate this value. 18 into 3.75 divided by 28.96 multiplied by 101.325 minus 3.75. Okay, so we are getting 0.0238. Okay, so this is the specific humidity, that is nothing but the mass of moisture per unit mass of dry air. Okay, this is what we had to calculate. This is mass of moisture or water vapor in kg per kg of dry air, right? So let us check the options. We are getting 0.023. So yes, option A, 0.023. This should be the correct option. Okay. So I hope this is clear, and we can move to the next question. Even if you don't know the formula, if you forget the formula, you can quickly grab all the formulas uh, in the psychrometry topic, because they are very you know, easy. Okay. So question 4. So it is saying the bypass factor of cooling coil blank space with blank space in the velocity of air passing through it. So it is there are a few options: decrease, increase, increase, decrease, remain same, and something. So it is saying if you change the velocity of air passing through the coil, then what will its impact on bypass factor of cooling coil? To answer this question, you should know what is bypass factor, right? So you know that you can have some cooling coil, okay, that will have some temperature. Let us say the temperature of cooling coil or heating coil is Ts, and temperature of incoming air is T1, and air which is going out, that is at temperature T2. So you expect that temperature of the incoming air after coming in contact with coil, it should be, there should be heat transfer, and this temperature should approach Ts, right? If you have infinite time, then after infinite time the temperature of incoming air, that will be equal to Ts, right? If you have kept this air T1 into some box which has temperature Ts, then after infinite time this air will become at the temperature equal to Ts, right? But in this case of cooling coil, you know that you have finite time, right? So air is coming, so it is getting in contact with the coil, okay? So you can have some better arrangement of coil. So air is coming in the contact of coil, so temperature T1, so the air which was at initial temperature of T1, that will cool down, but it will not reach up to temperature Ts, okay? And it will exit at some temperature T2, okay? So there is some loss of cooling, right? Loss of cooling in case of cooling coil and loss of heating in case of heating coil. So quantification of that loss is something we call as bypass factor, okay? Bypass factor is defined as x is equal to T2 minus Ts divided by T1 minus Ts, okay? If T2 is exactly equal to Ts, then bypass factor will be 0, okay? So this means there is no bypass, right? And if T2 is equal to T1, this means bypass factor is 1. There is no heating or cooling, okay? So we want very less bypass factor, we want more heat transfer, okay? So I hope these basic concepts are clear, and now we should be able to answer this question. So it is saying that with the change in velocity of air, what will happen to the bypass factor? Okay, let us say we have increased the velocity of air, okay? If we increase the velocity of air, then we will have less time for heat transfer, right? So because of less time of heat transfer, there will be less heat transfer, and bypass factor will be more, right? So there will be more loss of heating or cooling, okay? So this means less heat transfer. So this means less cooling or less heating So this means more bypass factor, right? Or you can say increased bypass factor. Similarly, if you decrease the velocity of air, then bypass factor will also be decreased. Okay. I hope this question should be clear. So it is saying that if we decrease the bypass factor of, sorry, the bypass factor of coil will decrease with decrease in velocity, yes. It will increase with decrease in velocity, no. It will increase, sorry, the bypass factor will remain constant if you increase the velocity, no. It will increase if you increase the velocity of air, yes. This is also correct. Okay. So if we decrease the velocity of air, the bypass factor of coil will decrease. If we increase the velocity of air, then bypass factor will increase. Okay. Hope this is clear, and we will move to question number 5. Okay, question 5 says the ambient pressure, temperature, and relative humidity of air at a location are 101 kilopascal, 300 Kelvin, and 70% respectively. Okay, the saturation pressure of water vapor at 300 Kelvin is 3.6 kilopascal. The specific humidity in gram per kilogram of dry air is. Okay, so the similar question we have solved, so we will use the same method. Okay, so what will we do? First, first we will calculate the partial pressure of water vapor. That will be equal to relative humidity multiplied by saturation pressure at this given temperature. Okay, because this is the definition of relative humidity. This is PV divided by PS, right? Partial pressure of water vapor in the mixture divided by the saturation pressure at the given mixture temperature. Okay, so relative humidity is 70%, so 0.7 multiplied by the saturation pressure is 3.6 kilopascal. Okay, so this is 2.52 kilopascal, and we have to find specific humidity. The specific humidity we discussed, it is mass of water vapor divided by mass of dry air. Okay, so number of moles of water vapor multiplied by molar mass of water vapor divided by number of moles of dry air multiplied by molar mass of dry air. So mole ratio of mole can be replaced by ratio of partial pressures. Okay, and the molar mass of dry air as well as water vapor, you know. So you can write as 18 divided by 28 point, how much it is? 28.96. Okay, so this thing you calculate, it will come out to be 0.622 PV divided by partial pressure of air, and partial pressure of air is nothing but total pressure minus partial pressure of water vapor, right? So partial pressure of water vapor you have calculated. Okay, so this is very important relation. We will use it again and again. So just I will just highlight this. Okay, so PV we have calculated, so you can calculate this quantity. Okay, 0.622 multiplied by 2.52 divided by total pressure. Total pressure is how much? 101 minus 2.52. Okay, so it is coming out to be 0.0159 kilogram of moisture per kilogram of dry air. Okay, but we have to calculate this quantity in gram of moisture per kilogram of dry air, but we have in kilogram. So just multiplied by 1000, so you'll get 15.9 kilogram of moisture per kilogram of dry air. Okay, 15.9 is the correct value. So is there any option? 12, 16, 18, 20. So we are getting 15.9. So part B can be selected. 16. This is the closest value. Okay. I hope uh, this is clear and we can move to the next question. Okay. So question 6 says that dew point temperature is temperature at which condensation begins when the air is cooled at. So dew point temperature we have discussed, right? So you can answer this question, but if you forget what we discussed, then I will discuss it again. For example, you have mixture at some temperature. Okay, so this is your initial temperature. If you cool this mixture at constant pressure, then after some point you will reach at the saturation limit, right? This is the saturation point. And if you try to cool it further, then what will happen? The condensation will start. Okay, and this is constant pressure line. I should also mention this. This is okay. So if you cool further, then condensation will start. So this temperature at which the condensation start when you cool the mixture at constant pressure. So this temperature where condensation start, this is called dew point temperature. Okay. So dew point temperature is temperature at which condensation begin when the air is cooled at what? Constant pressure, right? So constant pressure. Okay. Okay. So I hope this is clear and we can move to the next question. Question number 7. Okay. Question number 7 says, referring to the following psychrometric process shown in figure. Okay, so this is the figure. Which of the following refers to humidification process? Okay, so first of all, we should know what is a psychrometric chart. So this is a psychrometric chart. On x-axis, we have dry bulb temperature. On y-axis, we have specific humidity. Okay, and there are some lines. For example, this line, and maybe there can be another line. These lines are relative humidity lines. Okay, and there are some constant volume lines, and there are some constant enthalpy lines. Okay, and so on. So humidification means omega increases, specific humidity increases, right? Humidification means increase in specific humidity. Okay, so increase in specific humidity means you will go from the given point in the upward direction. Okay, in the increasing specific humidity direction. Okay, so you start from point A and you go in upward direction in increasing specific humidity direction, then the process will be humidification. And where you reach at 2B. Okay, so in this given chart, the humidification process is represented by from 1 to 2B. Okay, so the part B is the correct answer. What about other processes? For example, I will write the name of all these processes. So 1 to 2A, 1 to 2B, 1 to 2C, 1 to 2, what is this? D, and so on. And last is 1 to 2F, let us say. So 1 to 2A is what? See, that dry bulb temperature is increasing and humidity is also increasing. So it is heating with humidification. 1 to 2B is only humidification. And 2C is cooling with humidification. And 2F is cooling without humidification. Okay, you can also go in the downward direction, that will be dehumidification direction. Okay, for example, 2G is there, 1 to 2G. So this is cooling with dehumidification. Yes. Okay, so for example, in summer season, what you need cooling. But when you reduce the temperature of your room, then what will happen? At the reduced temperature, what will happen? The relative humidity will increase. For example, if you see in this diagram only, if you go from point 1 to towards point 2F, so what you can see is, uh, from this point to this point you will reach, and these green lines that I have made, these are specific, sorry, relative humidity lines. So if you do only cooling, then relative humidity will increase. And for human comfort, we need a certain range of relative humidity. Okay, so if humidity is increasing, then you feel some, sweating type of thing, right? So what you need to do with the cooling, you also need dehumidification. Okay, so that relative humidity remains in the human comfort range. Okay, and in summer, sorry, in winters, when you are doing heating, then if you don't change the humidity, then relative humidity will be reduced. Okay, if you reduce the, sorry, if you increase the temperature, the dry bulb temperature, without changing humidity, then you feel dryness on your skin because of reduced relative humidity. Okay, so to keep the thing in comfort zone, okay, so if you want relative humidity to be in human comfort range, you will have to do humidification with the heating. Okay, so in winters, what we do, in winters we do heating with humidification. In summer, we do cooling with dehumidification. Okay, but anyways, in this question, we have been asked which process refers humidification. Okay, so process 1 to 2B is the humidification without changing temperature. Okay, so part B is the correct option. Okay, so question 8, it says one purpose of subcooling of liquid refrigerant to, okay, so it says what is the purpose of subcooling of liquid refrigerant. So in refrigeration process, there are four processes, and one process is cooling. Okay, and during cooling, we do subcooling. Okay, we have reached to saturated liquid, but we do cooling even more. Okay, we do further cooling to reach in subcooled zone. Why we do subcooling? So this we have to tell. Okay, so there are four options. One is saying to reduce the compressor work. So it has nothing to do with the compressor. Okay, it is saying to reduce the compressor discharge temperature. Part C says increasing the cooling effect. Part C says to ensure that only liquid, not the vapor, enters the expansion or the throttling valve or the capillary tube. So part D is the correct option. We do subcooling. We cool it even further so that we make sure that only liquid goes inside the capillary tube or the expansion or the throttling valve. Because if there is vapor as well, then there will be formation of bubbles or cavitation, and that can block your uh, expansion expansion device. Okay, so we don't want cavitation. Okay, so that's why we want to make sure that only liquid goes inside the expansion wall, not the vapor. Okay, so part D is the correct option. Okay, so if it is clear, then we can move to the question number 9. Okay, so question 9, it says psychrometry deals with. So it is very easy to answer this question. We have been discussing the question related to psychrometry itself, right? So what we have been discussing? We have been discussing a mixture of, water vapor and dry air. So psychrometry is the study of mixture of dry air and water vapor. So it deals with dry air or moist air or liquefied gases or none of these. So the correct option is moist air. Okay, moist air is the mixture of dry air plus water vapor. So of course, dry air is the air which has zero moisture. Okay, so this can also come under psychrometry, but part B is the most suitable answer. Okay, so moist air is dry air plus water vapor, mixture of water vapor and dry air. So psychrometry is the study of moist air. Okay, so if it is clear, then we will move to the next question. Question number 9 says, when the partial pressure of water vapor corresponds to saturation pressure of water at mixture temperature, then the mixture is said to be saturated. So we have to tell whether this option is statement is true or false. So it is saying that when the partial pressure of water vapor corresponds to saturation pressure of water at the mixture temperature, then mixture is said to be saturated. So it is true, right? It is just a definition of saturated mixture. So saturated mixture is something in which the partial pressure of water vapor is equal to its saturation pressure at the given temperature. Given temperature means the mixture temperature. Okay, right? This is saturation. And at saturation, we have relative humidity is equal to 100%. Okay, and the mixture temperature at saturation is equal to dew point temperature, and that is equal to wet bulb temperature, and that will be equal to dry bulb temperature. Okay, so at saturation, dry bulb temperature, wet bulb temperature, and dew point temperature, they all are equal. Okay, and relative humidity is 100%. Okay, we have discussed this earlier, right? So this should be clear, and we will move to the next question. Question number 11. It says the principle of dehumidification is when a moist air stream is cooled at constant pressure to a temperature, at what temperature, so that some condensation of water vapor can occur. Okay, so in dehumidification, what we are doing, we are cooling the moist air, and if you want to remove the water content, then what we need? We need condensation. Okay, because of condensation, we can remove the water. Okay, in the condensed form. But in order to condensation for a start, we should reduce the temperature below the dew point temperature, right? Then only the condensation can be started, right? So for dehumidification, we need to remove water using, okay, to remove the water, what we need? We need condensation. Okay, so this is one of the method. There can be other methods where there can be some water absorption by some adsorbent, but by removing water using condensation, you will have to reduce the temperature below the dew point temperature. Correct? So there are four options: below its dew point temperature, above its dew point temperature, below its wet bulb temperature. So the option should be option A. Below the dew point temperature, the condensation will be started at dew point temperature, and if you reduce the temperature below the dew point temperature, then there will be more and more condensation, and you can remove the water, and in this way you can achieve the dehumidification. Okay. I hope this is clear, and we can move to the next question. The next question says, evaporative cooling process employs a combination of cooling and dehumidification in which, okay, evaporative cooling. So what is evaporative cooling? In evaporative cooling, you are basically uh, injecting some water spray, and when the droplets of those that water spray, when they evaporates, then they take heat from the surrounding to uh, from the surrounding mean the from the moist air to get evaporated. Okay, so for example, uh, you can send the moist air from this end, and at some point you can inject some water spray. Okay, then this water spray will take up some heat from this moist air to get evaporated, and at the outlet you will get the cool moist air, right? Okay, so what is happening? First of all, there is evaporation. Okay, so for evaporation you need to provide the latent heat, right? Because water vapor is being added in this moist air. Okay, so at the end you will get more humidity, more specific humidity, because you have added some water vapor, and the water vapor will bring the latent heat with it, right? Because when you change the phase of water from liquid to vapor, you have to provide latent heat. Okay, so for evaporation you need to provide latent heat. Okay, and cooling means reducing the temperature. Okay, reducing the temperature, and that temperature which you can feel, that is called sensible uh, heat associated with the temperature which you can feel, that is called sensible heat. Okay, from the name itself it is clear that the sensible heat, this can be felt, right? This can be felt. Okay, so that is why it is called sensible heat, because you can touch it and you can feel whether it is hot or cold. Okay, so in cooling you are reducing the sensible heat. Okay, so you are removing the sensible heat, so sensible heat is removed, and in evaporation latent heat is added. Okay, so latent heat, so latent means something which you cannot see, which something which you cannot feel. Okay, so you are adding latent heat during the phase change process. The temperature is constant. Okay, when the temperature is constant, then you cannot feel the change. So that is why this heat which you are adding during the phase change process, that is latent heat. And cooling means something which you can feel because of reduced temperature. So heat associated with the cooling or with the reducing the temperature, that heat is called sensible heat. So you are removing the sensible heat and you are adding the latent heat. Okay, so cooling is related to sensible heat is removed, so this means cooling, and latent heat is added, this means evaporation. Okay, so during evaporative cooling the sensible heat is removed and latent heat is added. Okay, so part B should be the correct option. Okay. Okay, so I hope uh, this is clear, and we can move to the next question, question number 13. Okay, so in cooling water, sorry, cooling tower. In cooling tower, water is cooled by the process of condensation or fusion or evaporation or sublimation. So you can easily answer this question. For cooling, you need to remove heat, and to remove heat, what you will do? Will do evaporation, because evaporation will require latent heat, and that latent heat will be taken from the moist air, and you will get the cooling effect. Okay, so basically there are cooling towers you might have seen in many plants, power plants, some hyperbolic structure, big structures. They are quite, high, sometimes even like 100-meter high. Okay, so they are basically cooling towers. Okay, so in cooling tower, what happened? The water spray, the water is sprayed. So for evaporation, it takes heat from the moist air. Okay, air comes in. So for evaporation, the latent heat is taken from the air, so air becomes, cold. Okay, and this hyperbolic structure is provided to provide good strength to these buildings, and this has nothing to do with the thermodynamics, this hyperbola shape. And these big structures are made so that the flow of air does not require any uh, external device, for example fan. Okay, so sometimes when the natural flow of air is not possible, then you'll have to use some forced flow type. Okay, but anyway, in cooling tower, the water is cooled by evaporation. Okay, so question 14 says air washers are used in air conditioning systems. Okay, so air washers are used in air conditioning system for what purpose? They only clean the air. Part B says they only clean air and they cool the air. Part B says they do humidification, heating, cooling, dehumidification, and clean the air. And last part says only dehumidification and humidification. So the answer is part C. These water washers are used in, many industries for air conditioning purpose, and they can do all these things. They can do humidification, they can do heating, they can do cooling, they can do dehumidification, and they do the cleaning of air. Okay, I will show some pictures of these water washers. So here is one such air washer. Okay, so it is air washer, not the water washer, sorry. Okay, and here is some, schematic. So here you can see there are many components. Okay, lot of component 1, 2, 3, and you can see what each components mean. So there is supply fan, fan pulley, inlet valve, supply motor, motor pulley, V belt, return fan, V belt, and lot of other components. Okay, so these can be used for heating, cooling, humidification, dehumidification, and of course cleaning the air. Okay, so cleaning the air means the pollutants and dust particles and other pollutants, they will just stuck in the wet surface or in the moist air. Okay, so they will be trapped by moist air basically. Okay, question number 15. It says wet bulb temperature is the minimum temperature to which moist air can be cooled under ideal conditions in a spray washer. So answer is true, right? Because wet bulb temperature is the minimum temperature which you can achieve by this evaporation, right? So this wet bulb temperature is less than dry bulb temperature that we have discussed. So you might have you all of us have seen lot of examples of this effect. Okay, for example, in your households, you many of us use coolers. In cooler, there is fan, but in the walls of the cooler, we are uh, doing the water supply, and the water is getting evaporated, and because of the evaporation, the we are getting the cooling effect. Okay, sometimes we put some wet cloth on our head when we are going outside in the summer season, again for the same reason, because we want cooling effect because of evaporation, and we get the reduced temperature. And if we are getting a perfect evaporating condition, then we will get the wet bulb temperature. Okay, so again, this is thermometer. At the thermometer, if you put some cotton, wet cotton, and you just swing it, then because of evaporation, this end will get cooled and you will get wet bulb temperature, right? So same thing we also do. We put some wet cotton on our head and we get cooling effect. But of course, we are not thermometer, but we can feel the cotton, you know, cooling effect. But anyways, so the wet bulb temperature is the minimum temperature to which the moist air can be cooled under ideal condition in a spray washer. So this is the correct option, true statement. Okay. Question number 16. It says cooling range in cooling tower is the difference in the temperature of hot water entering and cold water leaving. So as we discussed, what is cooling tower? So cooling tower, there is hot water coming inside, okay, and water is sprayed, okay, and at down we we have this cold water, okay, and we have air, and this air will leak from top, okay, and this moist air that is lighter than air, so it can go go to the environment, okay. So that this is the temperature of hot water, this is the temperature of cold water, so this difference is called cooling range. Okay, so the statement is correct. Okay, sometimes we use fan, sometimes you use, you know, big uh, natural draft towers. Okay, so question number 17, it says that a 5 mm by 5 mm by 3 mm room, as shown in this figure, not mm, sorry, meter, 5 meter by 5 meter by 3 meter room, as shown in this figure, contains air at 25 degrees Celsius at 100 kilopascal at relative humidity of 75%. We have to find the partial pressure of dry air, okay, specific humidity and enthalpy per unit mass of the dry air, and the masses of dry air and the water vapor in the room. Okay, so we have discussed similar questions, so this would be easy to solve. Okay, so part A, we have to find partial pressure of dry air. partial pressure of dry air will be equal to total pressure. Okay, so this is partial pressure of P as partial pressure of dry air will be equal to total pressure minus partial pressure of water vapor, right? So total pressure is given, we need to find the partial pressure of water vapor. Okay, now how to find the partial pressure of water vapor? Using the relative humidity, right? Relative humidity is given. So relative humidity is given 75%, and relative humidity is defined as the actual mass of water vapor present in the mixture in the moist air divided by maximum mass of the water vapor that can be present. So that is the okay. So in terms of pressure, you can write it as partial pressure of water vapor divided by saturation pressure at the given mixture temperature. Okay, so saturation pressure at 25 degrees Celsius, we need to check from the table, right? Because it is not given in the question. So you'll have to use the table. So this is yes, saturation table at 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 what temperature? 25 degrees Celsius, right? Okay, here we are at 25 degrees Celsius. We have saturation pressure is equal to 3 point. Saturation pressure at 25 degrees Celsius is 3.1698 kilopascal. Okay. So from this equation, we can find the partial pressure of water vapor. Okay, so it will be equal to 0.75 multiplied by 3.1698 kilopascal. You're getting 2.38 kilopascal. This is the partial pressure of water vapor, right? But we had to find the partial pressure of dry air. So partial pressure of dry air will be total pressure minus partial pressure of water vapor. So P minus PV, P is how much? 100 kilopascal. So 100 kilopascal minus 2.38 kilopascal will be the partial pressure of dry air. Okay, if you subtract this value, then it will come out to be 97.62 kilopascal. Okay, please check this value. If you are getting something else, just let me know. Okay, so this is the answer of first part. In the second part, we have to find the specific humidity. Specific humidity is, we have discussed it many times, it is the mass of water vapor divided by mass of dry air. Okay, so we have also find that relation that it can be calculated using this relation 0.622 into PV divided by P minus PV. Okay, so how it came? It came from the simple relation because of mass of water vapor can be written as molar mass of water vapor multiplied by number of moles of water vapor divided by moles of molar mass of dry air into number of moles of dry air, and instead of the ratio of moles we can use the ratio of pressures. Then molar mass of water vapor, we know it is 18, and molar mass of air, dry air, is 28.9 something, and partial pressure of water vapor is PV, and partial pressure of dry air will be total pressure minus partial pressure of water vapor. So it will come out to be 0.622 into PV divided by P minus PV. Okay, so this relation we are using. Okay, so if you just substitute the value, then you will get PV we have already calculated. So it is 97.62 divided by 100 minus 96.62. Okay, so this will be our specific humidity. 0.622 into 97.62, 100 minus 97.62. So it is coming out to be 25. Sorry, 97.62 is the partial pressure of dry air, not the water vapor. We need to use the correct value of partial pressure of water vapor is 2.38. 2.38. 100 minus 2.38. Okay. I'm sorry. 0.622 multiplied by 2.38 divided by 100 minus 2.38. So we are getting 0.01516 kilogram of water vapor per kilogram of dry air. Okay. So this is the specific humidity. What else we have to find? We have to find the enthalpy per unit mass of dry air. So total enthalpy divided by mass of dry air. The total enthalpy will be enthalpy of water vapor plus enthalpy of dry air divided by mass of dry air per unit mass of dry air. Okay, so enthalpy of dry air can be written as so this thing can be written as HA, that is enthalpy of dry air per unit mass of dry air. So this is specific enthalpy of dry air actually. Okay, into omega, that is specific humidity, multiplied by specific enthalpy of water vapor, right? Okay, and this thing is nothing but So you have H equal to omega HV plus HA. Okay. So HA you can find from the, again, you'll have to use some table. Okay. So for HA, you will have to use the property table of air. Okay. So this is air at 300 Kelvin. So in this question, also we have very near to 300 Kelvin. So you can use the same value CP 1.005. Okay. For HA, this will be CP into T 1.005 into temperature. And if you substitute the values, you'll get 1.005 into 25 degrees Celsius. And omega, you have calculated 0.0152, and HV, specific enthalpy of water, that will be sorry, specific enthalpy of water vapor, that will be equal to specific enthalpy of water vapor, saturated vapor at this given temperature. Okay, so we will have to check the water vapor table. At what temperature? 25 degrees Celsius. Okay, so specific enthalpy of water vapor, saturated vapor. Uh, this is 2546. This is 2546.5. Okay, so this is Hg at 25 degrees Celsius. Anyways, now we just need to substitute the values and we will get this thing, 1.005 into 25 degrees Celsius. I will not writing the units. Let us write the units as well. 0.05 kilojoule per kg degree Celsius into 25 degrees Celsius plus 0.0152 into 2546.5 kilojoule per kg. Okay, and if you calculate this value, it will come out to be it is coming out to be 63.83 kilojoule per kg. Okay? Kilojoule per kg of dry air. So this is our enthalpy per unit mass of dry air. What else you have to find? Mass of dry air and water vapor in the room. Okay, so mass is equal to, mass is volume multiplied by density. Volume is given, that you can calculate from the dimensions. Okay, dimension of the room is given, and density you can calculate from the uh, ideal gas equation. P is equal to rho RT. Okay, so the mass will be, so density will be P divided by RT. So the mass will be P by RT into volume, right? So for mass of dry air, you need partial pressure of dry air into volume of dry air divided by gas constant for dry air into mixture temperature. Okay, so partial pressure of air we have calculated, and this was 97.62 kilopascal. Volume of dry air, that will be same as the volume of this room, that will be 5 into 5 into 3, so that is 75 meter cube. Okay, it's equal to volume of the room. Okay, so multiplied by 75 meter cube divided by gas constant for dry air, that I am taking 0.287. Okay, that is not given in this question, I think, but you can check this value in tables, or otherwise these values are usually given in the questions. Kilopascal meter cube per kg Kelvin into the mixture temperature is 25 degrees Celsius. 25 degrees Celsius you need to convert into Kelvin, so it will be 298 Kelvin. Okay, sorry. So it is coming out to be, mass of dry air is coming out to be 85.61 kilogram. Similarly, we can find the mass of moisture or the water vapor. So mv will be equal to partial pressure of water vapor into volume of water vapor divided by gas constant for water vapor divided by temperature, mixture temperature. Okay, so partial pressure of water vapor we have found, and it was coming to be 2.38 Kelvin. Sorry, 2.38 kilopascal. This volume we have found, this is 75 meter cube divided by the gas constant for water vapor. I am taking 0.4615 kPa meter cube per kg Kelvin. You can check this value in tables, and temperature is of course 298 Kelvin. 2.38. Okay, so neat is coming out to be 1.2979 something. Okay, so we can round off this value, so it is approximately 1.3 kilogram. Okay, so this is the mass of moisture, this is mass of dry air. Okay, so this is what was asked in the question. We have to find the partial pressure of dry air, we have to find the specific humidity, enthalpy per unit mass of dry air, and the mass of dry air and water vapor. That's so all these quantity we have calculated. Okay, so I hope everything is clear, and we will see next question. So question number 18 says the dry and wet bulb temperature of atmospheric pressure at 1 atm pressure are measured using ceiling psychrometer and determined to be 25 and 15 degree respectively. Okay, so we have discussed what is dry bulb temperature and wet bulb temperature. So this is a ceiling psychrometer. So ceiling psychrometer is a device which can be used to measure the humidity using these two quantities, wet bulb temperature and dry bulb temperature. So here we have two thermometers. Okay, so one on the bulb of one thermometer we have uh, put the wick. So wick is nothing but the wet cotton, and there is one dry bulb. Okay, so the dry bulb will give the dry bulb temperature, and this wet bulb will give the wet bulb temperature, and the wet bulb temperature will be lesser than the dry bulb temperature. Okay, so from the dry bulb temperature and the wet bulb temperature you can calculate the humidity. Okay, so okay, so we have both the temperatures. Dry bulb temperature it is 25 degrees Celsius, wet bulb temperature it is 15 degrees Celsius, and we have to find the specific humidity. I will not solve this question, but I will tell how to solve so that you can solve it by yourself. Specific humidity you can calculate using this relation. This relation is derived using energy balance, and how to derive is, for example, uh, you have a adiabatic chamber. So here you have air, moist air, and this is a water bath, and from there you are getting the saturated mixture. Okay, so to get the saturated mixture, this bath should be really big, but you know we are using an imaginary water bath. So here you are getting the moist air of which you want to measure the humidity. Okay, so this is your sample. Okay, so this is a sample for which you want to measure the humidity. This you have saturated mixture, and here you can use a thermometer. So this will give you a wet bulb temperature, and outside you can use a uh, dry bulb temperature. So from the energy balance of how much water is evaporated from the mass balance of coming inlet water, sorry, mass of mass flow rate of inlet mixture, mass flow rate of this mixture at exit, and how much water is evaporated using the energy balance, you will get this relation. And I think this is explained in the lectures, or otherwise you can refer any standard textbook, you will find this relation. Okay, okay, from this lesson you can find the specific humidity and relative humidity. You know how to calculate, and yes, some values are not given, so for that you'll have to use the property tables. Okay, properties for air, properties for water vapor you can find from the table, but I am telling how to, I will just explain how to calculate the values which are asked. Okay, so relative humidity can be calculated from this relation. Okay, and okay, so this W1 will come from here. Okay, so this W is W1. Okay, so W1 can be calculated from here, and P2 is given. P2 is, if it is not given, you just take this value. Okay, it is given here. This is P2. Okay, and W1 again from uh, omega 1 from the part A. Okay, and temperature, sorry, the saturation pressure you can find from the table. I am writing the value, just calculate it. And enthalpy, this will be enthalpy of dry air plus enthalpy of water vapor, and enthalpy of this dry air, this can be calculated from Cp into T, and this can be calculated from omega 1 into specific enthalpy of saturated vapor at the given temperature. Okay, so this is how you calculate the values. I will write the answers so that you can calculate and check if you are getting the correct values. Specific humidity, this is 0.00653 kg H2O per kg of dry air. The relative humidity I, this will come out to be 0.332 or 32.2%, and enthalpy, this will come out to be 41.8 kilojoule per kg of dry air. Okay, so I request you to please try to solve this question yourself using these relations, or you can start from the basic. You can try to drive this equation. Okay, and some values are not given. For those, you can use the property tables and you should get these values. If you are not getting, if you have any doubt, then of course we can discuss in the next session. Okay, we have few more questions. So again, I will not solve, but I will tell you how to solve, and I will tell the answers. Okay, so I will quickly read it. An air conditioning system is to take in outdoor air at 10 degrees Celsius, 30% relative humidity at a steady rate of 45 meter cube per minute, to condition it at 25 degrees Celsius, 60% relative humidity. Outdoor air is first heated 20 degrees Celsius in the heating section, then humidified by injecting the hot steam in dehumidifying section. Okay, so what this question is saying is there is some air conditioning system which has to take some outdoor air. Okay, so let us say this is our system. So From outdoor, this is taking some air. Okay, so outdoor conditions are 10 degrees Celsius and relative humidity is 30% and volume flow rate is 40 45 meter cube per minute. Okay, then the outdoor is first heated. Okay, so there should be some heating coil. Okay, so it is heated up to 20 degrees Celsius, 22 degrees Celsius. Okay, so here the temperature T2, it becomes 22 degrees Celsius and then humidified. Okay, so then there should be some humidifier. Humidifier is nothing but some system which can inject the water sprays. Okay, so humidified of the hot steam in humidifying section. Okay, and the outlet conditions should be 25 degrees Celsius and 60%. Okay, so this is the required or desired conditions. Okay, so what you can do is you have conditions at inlet, you have conditions at outlet. Okay, so you can just assume this as a system and you can use conservation equations. Okay, mass conservation, energy conservation equation, and you will get the values. Okay, okay, so what we need to find? We need to find the heat supply and the mass flow rate of steam required in the section. Okay, so how will you find? You will use mass balance for dry air and water vapor, and you can use energy balance. Okay, this is one approach. You can try to solve it in some other way as well, but ultimately you should get the same answer. Okay, and answer for this part is, I'm writing the final answer. It will come out to be 673 kilojoule per minute. Okay, again I request you to please try to solve this question. I'm running out of battery, so that's why I'm rushing, because it can be stopped, the meeting can be stopped in between. And in part B, we have to find the mass flow rate of steam. Okay, so again, the mass balance for water. Okay, okay. Again, I will write the final answer for you. You should get, okay. And we have one more question. The cooling water leaves the condenser of a power plant and enters a wet cooling tower. So what is a wet cooling tower? So in wet cooling towers, you are spraying the water. Okay, there are water sprays. In dry cooling tower, there are not the there are not the sprays, but you have some coils where uh, cold water flows. Okay, so we have wet cooling tower. So there is water spray. Okay, so the cooling water enters wet cooling tower at 35 degrees Celsius. Okay, so here it is entering at 35 degrees Celsius at rate of 100 kilogram per second. At the rate of 100 kilogram per second. Water is cooled to 22 degrees Celsius. Okay, so it is cooled to 22 degrees Celsius. So it is by air. So air enters the tower at 1 atmospheric pressure. So air is entering at 1 atmospheric pressure, 20 degrees Celsius and 60% relative humidity, and leaves the tower at 30 degrees Celsius and in the saturated conditions. Saturated conditions means relative humidity will be 100%. Neglecting the power input to the fan. Okay, so there is fan for the circulation of air. So the power input to the fan that we can neglect, that is given in question. We have to find the volume flow rate of air into cooling tower and mass flow rate of required makeup water. So this is new term, makeup water. So there will be some evaporation of water. So whatever amount of water is being evaporated and being lost into the environment with the air, that much water should be added. Okay, so this will be equal to water to replace, compensate for the evaporated water. Okay, so it is similar question. So again, we will have to use the mass balance for the dry water, so dry air and water. Then energy balance. Okay, then you will get some equations. Then you can solve those equations. If some values are not given in the question, then you can use the property tables. And after solving, you should get MA, mass flow rate of dry air, equal to 96.9 kilogram per second. Okay, so the volume flow rate will be MA into specific volume, and that will come out to be 81.6 meter cube per second. Okay, so this is what we have to find in part A. Okay, so this is the answer for part A. In part B, we have to find the mass flow rate of makeup water. Okay, so uh, how to find the mass flow rate of makeup water? So as we discussed, that makeup water has to be added to compensate for the evaporated water. Okay, so how much water is evaporated, that you can find from the difference of humidity at inlet, air inlet, and the air and the humidity of air at the outlet. Okay, so humidity of air at inlet is omega 1 and humidity of air at outlet is omega 2. So the difference of this thing multiplied by uh, mass flow rate of dry air, so this will be equal to evaporated water. Okay, evaporation rate, water evaporation rate, and this will be same as the mass flow rate of makeup water. Okay, and this value will come out to be, I'm writing the final value, ma, you will find from the part A, 96.9 kilogram per second, and omega 2, that is the humidity at outlet, that is 0.00273, minus at inlet it is 0.0087. So this will come out to be mass flow rate of makeup water. This will come out to be 1.80 kilogram per second. Okay, So you can see that warm water was coming at the rate of 100 kilogram per second, but makeup water is being added at the rate of 1.80 kilogram per second. Okay, so it is like this much water is being evaporated. Okay, so around 2% water is being evaporated and 98% water is, you know, it is saved. Okay, and that is circulated, recirculated. Okay, so I'm sorry that I rushed in the last 2 3 questions, but these are the answers. And as I explained how to solve this question, you can try to solve by your own and try to see that if your answer matches. So this is all for today. We discussed the evaporative cooling, the wet bulb temperature, dry bulb temperature, relative humidity, specific humidity, dew point. Okay, we discussed how to what is the relation between these uh, partial pressures and relative humidity. Okay, we discussed what is bypass factor, how it is dependent on velocity of air. Okay, we solved some questions related to this specific humidity and partial pressures. Okay, we discussed that dew point temperature is the temperature at which condensation begin when the air is cooled at constant pressure. We discussed how to use this psychrometric chart and how various processes can be plotted on this chart. Okay, we discussed that we subcool the liquid refrigerant so that there is no cavitation in the expansion device in the capillary tube. Okay, we discussed that at saturation, their relative humidity 100%, dew point temperature, wet bulb temperature, and dry bulb temperature, they coincide. Okay, they are equal at when the saturation is achieved. Okay, we discussed that during evaporation cooling, the temperature is reduced, so sensible heat is removed. But since there is evaporation, so you are adding latent heat. We discussed the cooling tower. Okay, we tried to solve some questions. Okay, and please note this question, or you can take the screenshot and you can take the write the answers. Okay, so that you can solve by yourself and match the values. Okay, so we will stop here and we will meet in next session. Till then, take care. Thank you.